Hello, AP Chemistry students, and welcome to Solubility Equilibrium, page 4, exercises 3 and 4, with me, Mr. Regan, in a red theme today. If we start on page 4 at the top, we are seeing that we're trying to estimate the salt solubility from the KSP. And what we're trying to do is figure out in moles per liter, or molarity, how many moles or how much stuff can dissolve in water before you start seeing the solid not dissolve anymore. And so if we have something like 1 times 10 to the negative fourth, that's going to be pretty soluble and it will dissolve easier. Whereas if we see something like 1 times 10 to the negative 30th, that's going to be very insoluble, and we're just going to see a lot of solids still. That's not going to dissolve once you put it in water. So if we think of NaCl, it has a pretty low solubility value. And if we look at some other things, if we look at the table on page 2, you can see that things do have values similar to this or even smaller than that. So what we're trying to do in these problems is figure out how much of this stuff can we put into water before it doesn't dissolve anymore and it just forms a solid. So let's begin by doing this first problem with calcium carbonate. And before we do that, we need to know which ions calcium carbonate breaks up into. Thinking of your polyatomic ions, you should know that the first one of them should be CO3 minus 2, and the second one should be calcium plus 2. No coefficients here, except for 1 to 1 to 1. At this point, we can write our KEQ, which is our KSP, which is 3.8 times 10 to the negative 9th, and that is equal to your products raised to their coefficient. So this is just Ca plus 2 raised to 1 times CO3 minus 2 raised to the 1. At this point, we are not given any mathematical values for our calcium or our carbonate. Because we know that they both need to be the same value, because it's a 1-to-1 ratio, we can give them the same variable, and that same variable is going to be x, like we've done before. And once we say that x times x, we can call that x squared, and we can solve for x using this value here. So let's set that up. 3.8 times 10 to the negative 9th equals x squared. Therefore, x is the square root of 3.8 times 10 to the negative 9th. You can pause, give yourself a minute to solve for that. And the value for x is 6.16 times 10 to the negative 5th molar. And if we want to plug that back in, knowing that each of our values for x is a 1-to-1-to-1 ratio, we can say that the solubility of calcium carbonate is x, which is that value. And this is moles per liter for molarity. And if we want to determine how soluble it is in grams per liter, we just do a little bit of stoichiometry. 6.16 times 10 to the negative 5th moles per liter. Knowing that we need to cancel the moles, getting to grams of calcium carbonate. Calcium has a molar mass of around 40, plus carbon's 12, plus 3 oxygens is 48. And so this is very close to 100 grams. All we're going to do, how about some mental math here? If we're multiplying this by 100, we're going to be moving the decimal point to the left, or to the right 3 times. And so this is just going to be 6.16 times 10 to the negative third grams per liter of calcium carbonate. Moving on to the next problem, it's going to be very similar, and so this is exercise 3. We are given a KSP value for copper 2 iodate, CuIO32, with a value of 1.4 times 10 to the negative 7th, and we want to calculate its solubility for this substance here. And we can again break it up into its ions, in this case being Cu plus 2 and 2IO3 minus. We can say to 1 to 2 ratio. And just like the last problem, we are looking to solve for a value for this. So we need to plug in some x's. So this would be x, this would be x, and this would be 2x. And we can say that our KSP equals Cu plus 2 times IO3 minus squared. We can't forget this squared here. And if we want to write it in terms of x's, we can say that it equals x times the 2x from here, and we still have to square it. Remember from earlier in equilibrium that this is the quantity of 2x squared, and so we have to square that 2 also. So this becomes 4x squared times x, or our KSP equals 4x cubed, with our value being 1.4 times 10 to the negative 7th. And if we want to solve for x, we can do a couple steps in a row here, dividing by 4, taking the cube root, and I'll write this as x equals the cube root of 1.4 times 10 to the negative 7th over 4. Pause to give yourself a minute to calculate this if you need to. And we get a value of x equals 3.3 times 10 to the negative third moles per liter. And we just want to make sure that we double check what our x actually is, because we are solving for the solubility of that copper 2 iodate. And if we look at x and we go back up above, x actually is our value. So we can say that the molar solubility of copper 2 iodate is this. Again, if it asks you to convert that from moles per liter to grams per liter or grams per milliliter, you can take the value 3.3 times 10 to the negative third moles per liter and 1 mole of the compound. In this case, for copper 2 iodate, the molar mass is 413.35 grams. And if we want to convert our liters to milliliters, we can. And we get a value of 0.0014 grams per milliliter. And if we actually take that back to liters, that is 1.4 grams per liter. So 1.4 grams is not a lot. So if we weighed 1.4 grams of this solid and put it into a liter of water, that's all that would dissolve. If we tried to put any more in there, it would stay as a solid. So this is not very soluble, so we wouldn't be able to get a lot of this solid to dissolve in your liter of water. Last problem in this set is solubility in common ions. Common means things that have things that are being shared. And if we want to take a look at this problem, it says calculate the solubility of solid calcium fluoride in a 0.025 molar solution of sodium fluoride solution. Common. What do you see in common here between calcium fluoride and sodium fluoride? Hopefully you see that both of them have that F in there. And so let's break this down into its component ions again. The calcium fluoride breaks up into Ca plus 2 and F minus, 2 of them, with a 1 to 1 to 2 ratio. We can give this X to X to 2X treatment again. And if we do similarly for sodium fluoride, we get Na plus and F minus with a 1 to 1 to 1 ratio and an X to X to X ratio. So we want to figure out where to start here. I know that I need to end with this calcium fluoride. This is what I'm looking for here. I'm looking for this X value. And what we need to do is that we know that the common thing here is my F, or F minus to be more specific. And what we're given is that we know the F minus, or we know the NaF value. So it's not actually X here, we're actually given a value for it. And so we can use that to say that we know the F minus value. From this F minus value we can use that over here, and then we can solve for X from there. So it takes just a couple other steps, but let's do that. So if we want to plug in this number, get rid of the green for now, we are told that this 0.025 is this value. So because of this 1 to 1 to 1 ratio, this is also 0.025 and 0.025. If we want to now relate these two equations, we can say that the F minus concentration there comes over here, and we can say that this is 0.025. We cannot say in this instance that this would be half, or 0.025 over 2, and this would be 0.025 over 2. We cannot say that because these are two different compounds. We know the F minus part of it, but the Ca and the CaF2 are completely different. So what we need to do is relate them with the F minus, but also using something that relates to the CaF2, which is its KSP value. When we have a KSP value, we need to set up an equation that uses the KSP. So that is KSP equals my Ca plus 2 times my F minus squared. From there, I know this value, and I can solve for the Ca plus 2, and if I know this, then I can then solve for that. So that is what we're going to do. And so we can say that Ca plus 2 concentration equals F minus squared over KSP, which is, I'm going to use a different color, boring black, 0.025 squared over 4.0 times 10 to the negative 11. And that gives me a value of 6.4 times 10 to the negative 8th molar. And so that's my Ca plus 2 ion concentration. And I know that if I'm trying to solve for this overall, and these are a 1-to-1-to-1 ratio, that my Ca plus 2 is equal to my CaF2, and is 6.4 times 10 to the negative 8th molar. I hope you found these videos helpful. For some more solving of KSP equations, please email me if you have any questions, and try the problems in the book that correspond to these questions. Thank you. See you soon.